In the next section, we'll look at some of the more immediate solutions for the RMQ problem. And we'll see that these are actually building blocks we need later on for the sophisticated version. It will be, again, in a way, the final solution will not be some genius insight and then the rest just falls in place. It will be a cool technique, but then building on the simpler things that we discussed first. And I don't know if you've spotted this pattern that happened in other places too. So it's maybe also a way to advertise for always try the simple things first, put down what you can easily achieve and see how far that gets you. And then you have a repertoire to come back to. Okay, I'll make this more concrete. But let's do the very, very simple things first. It's a problem where we have something at pre-processing time, something at query time. Let's edge out the extreme cases first. We can either do nothing at pre-processing time, right? Then all we have left at query time is to just go through the array and find the smallest element. So that's a linear scan of this range. You just go through, find the minimum. You all know how to code that by now, I guess. So that's not hard to do. But of course, the query in the worst case is the entire array or almost the entire array. And then you need linear time for the queries. But you could even say you spend 0 time at preprocessing. But let's be generous and call that constant time, just returning. OK, that's not too useful because the queries are very slow. The other extreme is I don't want to spend any thought on the query side. I can do that if I have pre-computed all answers. So this is not completely out of the question. You could have a big array, a two-dimensional array for all positions I and j. It can be a triangular matrix. We only need it for I less than j, but that's just a factor of 2, so that won't save us much. So we store in this array all the possible arrangement queries up front. We do everything at pre-processing time. Then the time to answer a query is just finding the position in the array. That's constant time then. But the query time is really slow. If you do it the naive way, you would have for I from 1 to n, for j from I to n, so a double loop. And then inside the loop, you do a scan like this. And so in terms of the big theta class, that's cubic. That's very, very slow. You can very slightly improve this to quadratic time instead, where essentially you compute each of these values in constant time now. And the reason why you can do this is a simple observation, but I think it's worth stating that. Suppose you have some range I to j. If you're smart about the order in which you compute the answers, you could say, OK, that range is some range with one more element. So I look up. Hopefully, I have computed that first, the range that ends one element early. And now there's really two options for the minimum of the entire range. The minimum can either be the new element or it's the old element, the old minimum in the left. So it can be the min in here or this one. So I have one comparison to make. I'll look up where the minimum is in the I up to j minus 1 range, pick out that element, and compare it to this one new last element. And whatever is smaller wins and gets the entry of that next entry. That way, you only spend constant time for each element to fill. That's better, but still a long way away from linear time. And I think this is all you can do with these very simple solutions. Now, if you think about this a bit, we kind of like this pre-compute all because it's very fast at query time. But maybe there's an option to not store every single query, because that not only costs us space, it also costs us the time to compute all the entries, or even write the entries at least. And so that's what the sparse tables do effectively. They have another observation about the nature of this problem that allows you to reduce what you store a bit more. We still have such a two-dimensional matrix, but the meaning of the entries will be a bit different. We only store an entry when the length of this range is a power of 2. Okay, like a shallow, superficial comment. Whenever always try powers of 2 first. They often work, but I mean, there's a reason in this case for that I'll show you in a second. But let's suppose we do that. How much does that help? We still have all starting positions I, but then we could say we don't have all right endpoints j. We only keep those that give us a power of 2. Because the range is bounded by n, there's only log n powers of 2 until you hit the end of the array. And so we have at most n log n entries. That's much fewer than n squared. And so if we want, we can store that in a different matrix. I gave it a different name to be clear. So it's m prime. And the meaning is as is defined here. So it's m of I. And then instead of j, we have I plus 2 to the k. OK? So we're still storing the explicit results of some arrangement queries, but only a small subset of them. But then how do you answer a query that's not at length a power of 2? And the trick here is that whatever your range is, you can cover it with 2 ranges that have length power of 2, so that they at least meet in the middle or overlap a bit. Now, why does that help? You can independently look up the blue range and the green range, so the power of 2 length range aligned left and aligned right in your range. And you will find that there's two answers from these. Those are the minima in the ranges in the green and blue range. And the minimum of the entire range has to be one of the 2. It has to be one of the elements somewhere. And every element either lies in the green range or in the blue range, or maybe even in both. And so formally, we can solve the RMQ query in this case by taking whatever is smaller, the minimum of the blue range or the minimum of the green range. And these, again, are looked up in our M prime table, because we can pick them so that the length is a power of 2. I guess I should fix this mistake here. There's a -1 because we count endpoints inclusive, right? That's corrected here. The blue range is very easy. You just start from I and add a power of 2. The green ranges, you have to start with j and subtract. So you get this left and right aligned. And so, yeah, I guess I don't know if I can squeeze that here. The trick is that this is m prime I k, and this one's m prime of this lengthy thing, j minus 2 to the k plus 1, and then k. So both of these, the green and the blue value, can be looked up in our sparse table. I guess I should have said that's where the name comes from. You're trying to store the original pre-compute all table, but in a sparse way. You only remember a small subset of the actual values, and you forget all the rest. Turns out you can reconstruct them at runtime with just one more comparison. All right? So that's the structure of the table we store. We also have to pre-compute that at pre-processing time. But you can do this with the same trick as before. If you're trying to fill this table, what that means is a range that starts at I and extends to the k positions. Well, I can cut that range in half. Then I have two ranges of the next smaller power of 2. And so you can again get that from this. We have to look up the values, but other than that, so we take m prime I and k minus 1. That's this range. And the second range is the one that starts later, so it's I plus 2 to the k minus 1, then k minus 1. The minimum in the entire range has to either lie in the left or in the right half, and this is the way to find out. That way, again, in the pre-processing step, you only spend a constant amount of effort for filling each entry. And so the pre-processing time is proportional to the size of this m prime array. Right, so without too much complicated techniques, we get this n log n pre-processing time, constant query time. Question?
Why can't we simply short the array rather than doing all of this pre-processing and find the things whatever we wanted?
So the question was, why can't we simply search the array?
Short, like from short the array, and then we are the goal is to find the minimum number.
Right.
So why can't we simply short there and find it rather than doing two?
Oh, sort the array.
Short.
Well.
Like merge short, bubble.
Yeah. Okay. The game is that you are not allowed to modify the array. And if you think about the, I think it's an important point. So this may become clear here. If you're trying to find the longest overlap between two of these suffixes, if you were to take this array and just sort it, you would completely lose the order. And so, I don't know, you would have maybe all the zeros up front. So you would get 0 overlap between these. So the connection is lost to what the array originally represented. So this is only interesting if you're not allowed to modify the array. In a sorted array, I guess, yeah, the range minimum in any range is just the leftmost position, right? Yeah. But the point here, if you want, something I didn't stress all that much, you can pretend the array is just read-only for what we're doing. Okay, so we get our pre-processing time and space down to n log n. And that's where, if you've been doing data structures for a while, you may get curious. This log n factor often can be removed with additional tricks. And we've seen this over and over already in this module. We've seen it for the parallel prefix sum, for example. We had this solution that had log n span, but then n log n work, whereas the sequential algorithm had linear work. And at the time, we applied a blocking trick and could get away from that n log n to linear. In a way, something similar works here too. Unfortunately, it's more tricky because there's still some problem left. So the solution will again use this sparse table solution as a black box on a smaller instance of the problem. Instead of doing it for the whole array of n numbers, we'll do it for something like n divided log n numbers. But you still somehow have to solve the original problem. And so that might not be so clear at first.